All right, well, hello physics students and welcome to this video lecture that's going to introduce us to this idea of rotational motion or rotational kinematics. So far we've talked about torque. We've looked at torque in terms of static equilibrium, but also now today we looked at it where torques actually start causing rotation. So we need to understand kind of the kinematics of rotational movement. So what I have here is a compact disc. Who even knows what those are anymore? And my center point of that disc is right here. Okay. Now I'm just going to draw some reference line over this way, and I'm going to mark a point right here that I'm just going to call point P. All right. Now I have a radius of this compact disc. We're going to say that radius is just R. Okay, now let's say that compact disc starts moving, okay, and we're just going to follow point P, and let's say that our compact disc starts rotating this way. Okay, so point P then might end up somewhere over here, and I'm just going to call that P prime. Okay, so we've moved some angular distance, we have some rotation there. Now we've covered this length, okay, of the circle, and we call that an arc length, and I'm just going to call that S. Okay, so S is arc length. But not only did we cover some arc length S or some linear distance here, but we also covered some angular distance. Okay, we covered some angular distance that I'm going to call theta. Okay, so we covered some angular distance that I'm going to call theta. And this is our first key with rotational motion. We have this thing called angular displacement. Angular displacement. Okay, and we're going to define that mathematically as theta. Okay, so this was our angular displacement right here. Theta is going to be equal to our arc length divided by the radius of that object. Okay. Now it should be it's important to know here that theta, our units for theta when we're talking about rotational motion are going to be in radians. Now before I move on too far, I want us to know that, let's say that P started here, okay, and it actually, we had one full revolution. We're going to say that one revolution is equal to 2 pi radians. Okay, and along with that, I just want to make sure that we remember this, that 1 radian is equal to 360 degrees divided by 2 pi, which is equal to 57.3 degrees. Okay, that's just from math. That's going to be important for us when we do some problems, that we know that kind of conversion factor there. So, big idea here is that angular displacement, okay, our angular displacement theta is equal to that arc length divided by the radius of that object. Okay, now we obviously had rotation here. So this thing started to move. So it had some angular velocity. Now, when we get into angular velocity and we get into angular acceleration, they're very similar to when we were doing just linear kinematics, okay? One-dimensional kinematics. So how we define this, we're going to say that angular velocity mathematically, we're going to say that it is omega is equal to our change in theta, okay, our change in angular displacement divided by time, okay? And we can extend this out further and we can say, we could say theta final minus theta initial divided by time. And now if we really wanted to take a look here, we could relate this to our 1D kinematics where we had velocity is equal to x final minus x initial divided by time. Okay, so you can kind of see the similarity here between this equation and this equation, but instead of x's now as our displacements, we have theta values. We have an angular displacement. Now our units for angular velocity, well, we have radians, we have radians up here, and we have seconds down here. So our units for angular velocity are just radians per second. Okay, now finally, let's say that this compact disc is really starting to get going now. It's going to start moving faster and faster and faster. It's rotating faster and faster and faster. Well, then we have angular acceleration. Okay, and we dealt with angular acceleration in that simulation that we did today. Now again, we can relate this back to uniform 1D kinematics, where we said that acceleration was equal to v final minus v initial divided by time. The equation that we have for angular acceleration looks very similar to that. We're going to say that alpha is equal to our change in angular velocity divided by time. Okay, and we can extend that out even further, and we can say angular velocity final minus angular velocity initial divided by time. Okay, now our units, we have radians per second up here, we have seconds down here, so our units for angular acceleration are simply radians per second squared. Okay, now rotational motion looks big and scary because we have all these new symbols. We're throwing in thetas, we're throwing in alphas, we're throwing in omegas, but really they're the same equations as we had for 1D linear kinematics, except now we're just using these different symbols which get us into rotation as opposed to moving in a straight line. So do not be intimidated by these new equations. Really, the big thing here, the big equations, this guy right here, angular displacement, angular velocity, and angular acceleration. Okay, we talked about angular acceleration, and we looked at angular acceleration in that demo today, and how angular acceleration can be caused by net torques. We're going to start utilizing angular velocity and angular displacement a little bit more. Now tomorrow, right away, we're going to talk about how we can relate these ideas of angular rotational motion to linear motion. Okay, discussing then linear velocity or tangential velocity, as we sometimes call it, and also linear acceleration, which you saw a little bit of today in that simulation as well. But I'm not going to overload you with that tonight. Come ready to work tomorrow, and have a good night, AP Physics students.